Right. So we said our acid chlorides are going to be our most reactive compounds. And so generally, if you want to form some kind of derivative, starting with the acid chloride is the easiest way because it's the most reactive. However, we can make acid chlorides out of less reactive derivatives, and specifically carboxylic acids are a good one to do it from. So we can just add our good old pal SOCl2, and we'll take a carboxylic acid into an acid chloride, and then you'll form side products of SO2, which is a gas. So that's the driving force of that. And then some HCl as well. Overall, here's the mechanism, right? Very similar to one of the ones that we've already learned with the amine. In this case, we're just going to have one of our oxygens, or the OH one, kick its lone pair down, form a pi bond, kick this pi bond onto this sulfur, and then kick that SO bond up, right? Very similar to the reaction we did a couple minutes ago. Get the intermediates. That's always the tricky part. Make sure you're not missing any charges or any bonds or anything like that. Hopefully I'm not. This thing comes down here, kicks off the chlorine, right? Nothing we haven't seen there. And now we have a Cl minus, and what we've done is we've created a good leaving group, right? We've got the SO2 right there, so that can act as a good leaving group eventually. And then we're also just going to do a proton transfer here to kick off the proton off this hydrogen, and then just have our chlorine attack, have this tetrahedral intermediate form. Don't kick off that SO2 just quite yet. Always form this tetrahedral intermediate. And then we just have this negative charge kick back down and then kick off SO2, right? So the chloride's going to leave as well. And then you've got your acid chloride, your SO2 gas, which can just go ahead and float away. And then you're good to go. Note that we have the tetrahedral intermediates, and note in this mechanism, we can have both positive and negative charges because we're doing this under relatively neutral conditions. And once you've got your fancy schmancy acid chloride, you can do a whole bunch of different things with it. And the reaction for each one is relatively the same. So for example, if you added some water to this, you could turn this into a carboxylic acid. Note that we oftentimes add a weak base to this. So in this case, pyridine is the most commonly used base for this kind of stuff. And basically the base is there to remove any HCl, really H+, so it doesn't react further. So it's just a sponge of H+ to make sure that that H+ doesn't go and react further with the compound. But obviously, right, we can switch it to all kinds of different things. So you can use water if you want a carboxylic acid, or you can use some kind of alcohol if you want an ester instead. You can use amines, HNR2, where these R's could be H's or they could be other things. Generally, we just use two equivalents of this, one of them to do the reaction, the other one to take the role of the pyridine and basically just act as an H+ sponge. We could do reduction reactions, of course, with lithium aluminum hydride. That'll reduce it all the way down to an alcohol, and you can't stop in between. If you did want to stop in between, you would just use a different reagent. It's very similar to the lithium aluminum hydride, except instead of having 4 hydrogens, we're going to have 3 OR groups, and these OR groups are usually bulky groups like a tert-butyl or something like that, and then only 1 H there. And we won't go into the mechanism or anything, but basically this stops us at the aldehyde. We could do Grignard reactions with this. which would take us all the way down to the alcohol and add 2 equivalents of whatever you're adding, right? So these R's come from the Grignard. If we wanted to just add 1 equivalent, we could use a milder reagent. So instead of using this magnesium bromide, we could use this R2 copper lithium. This is known as the Gilman reagent. And it's very similar to the Grignard. Except it's just milder. The bond difference between copper and carbon is less extreme than the magnesium copper bond. And so this will stop at this ketone where this R group came from your Gilman reagent. And then finally, we can use deprotonated carboxylic acids to basically just do SN2 reactions and make acid anhydrides. One thing I forgot to mention is with this alcohol reaction, sterics play a big role. So for example, if you had an alcohol that had multiple types of alcohols in it, or if you had multiple alcohols in solution, generally the less substituted alcohol will react the fastest, right? And that makes sense because the first and main step is obviously going to be attack of our carbonyl. So overall, a lot of mechanisms, a lot of different things you can do, but overall, they're mostly the same thing.